in the x dimension. So if x is between, greater or equal to nb, n's the number of wells, and less than n plus 1 b, remember little b is the separation of the delta wells, so with those conditions, so long as x is between here and here, then your wave function here is of this form. And you can look at it, it's somewhat similar to here, and if x is in this region, so x would be, to make it sound a bit plausible, so x would then be nb plus something, right? But you're subtracting nb each time, so effectively what appears here is the something, and that something is less than b, right? It's some distance less than little b. So it sounds somewhat plausible. Now, where on earth did this come from? Well, that's not at all that's not at all obvious just looking at it. Now, notice the I; it's a complex number, so this is of modulus of size 1. Okay, it's e to the I something, so it's going to be an oscillating phenomenon of some sort. Now, this k that comes, that's new. What's that all about? Well, it just comes out of Bloch's theorem. Just think of k as a constant, right? So k is like another constant. Like here you've got a and b, they're constants, and you've got this new constant, little k, right? Just think of it as another constant. Where it comes from, why, don't worry about it. You need to study Bloch's theorem to appreciate what it means, right? And that's the solution. Repeat, that is the solution. That's your wave function when you have n delta wells, and this is the wave function that exists between two neighboring delta wells. Okay. The nth. Now wait a minute. I've got to be careful here. Is this n here the total number of wells, or it's just the nth? I guess it's just the nth. Looking at this, so little n here is just the nth delta well. Okay, so you've now got three constants: a, b, and k. Now, so that's sort of like the heart of the appendix, that result, and the rest is pretty much deduction from this essential assumption of using Bloch's theorem. Now, the constraints, the conditions on the wave function, single valued, normalizable, continuous in value, continuous the gradients, blah blah, all that stuff. You can now apply to this, right? Now, oops. Now, the continuity conditions at each boundary, like at every delta well, at every b, little b, right? On the infinitely small distance to the left of the boundary, here, that value needs to equal the value at infinitely small distance to the left and the right of the boundary. So these two have to be equal, right? That's true at the n plus 1th delta well, right? So this is just continuity of the values, right? The two eigenfunctions either side of the barrier, either side of the delta well, and here we're using the difference in gradients. And instead of put it, well, in the text puts it in this form, just 2s. And S, remember, was just defined as 2m delta over h bar squared, right? Right, so you have the difference of the gradients from the previous session. So now it's just algebra, and you can do this yourselves, not so hard. So so given, here's your formula, here's your wave function for n at the nth. So put n plus 1 into here. So here you have n plus 1, here you have n plus 1, n plus 1, and so that with n plus 1 here has to equal well, this, with just n, at x equals n plus 1b. So the x here, you put n plus 1 times b, and you will get something like this, right? That's just algebra. So so do that. That's not too hard, right? So you'll get this one. Okay, now the difference in the gradients. So you need to differentiate this, where n is, so it's n plus 1 now, so you'll have here n plus 1, here n plus 1, n plus 1. So differentiate that, and then subtract it, well, when you differentiate this, when you just have n here, n, okay, and is equal to that, and then you'll get this expression, okay? So that's not too difficult. So just apply these two constraints, and again at x equals n plus 1b. So at the position of the nth, n plus 1th delta well. All right. So you'll get this second expression. So now you have two equations in a and b and k. So you've got a k here. So with two equations and three unknowns, so we've got the constants a, b, and little k. But with two equations, we can eliminate the a and the b. Right? So do that. Right? So you've got two equations, so you can solve for a and b, and that gives you one equation for the k, the little k, and that equation works out to be this one, where the cosine of kb equals the cosh hyperbolic function. I assume you're familiar with hyperbolic functions. When I was a little kid, well, not so little, I suppose, teenager, I suppose it's a standard schoolboy joke, the cosh and the shine were called the alcoholic functions. Old joke, right? So it's equal to cosh of, well, this expression here, square root of minus e, because e is negative, right, usually. So the square root of minus e, s minus 1 over square root of minus e times the shine, S-I-N-H, the alcoholic sign, hyperbolic sign. Okay, the shine of square root minus e times s. Right? So that's the equation that you get involving k. So you've got k's in it here. Once you've found values for a and b, and in terms of k, so you get this third equation. Now I've run out of board. This equation here now, from it, like this, the cos value, for example. Cos has limits, right? The maximum and minimum value of a cosine is plus or minus 1. So that's placing restrictions already on if this is limited to plus or minus 1, that's going to have implications for your e, solving your e. So in a hand wavy way, and I'll do this on the next session, which will be in the daylight. From this we will start to get the deduction of allowed and disallowed energy bands, which is so critical for the behavior of transistor. Alright, well that's as far as I can go because of the board. Let me make a general comment. I have now decided, I mentioned this in a previous session, now that I can upload to YouTube twice as fast thanks to the adjustment of the parameters, the compression software parameters as performed by my son-in-law. I've now decided to to do 3 sessions, record 3 sessions. So roughly, I don't know, somewhere between half an hour to an hour, usually around 30 minutes or so, and to do 3 of those a day. Now the realities are that probably 2 of them will be in daylight, unless I get up really early, but probably 2 of them will be in daylight, so the lighting on the board will not have the sort of bluish colour that comes from the artificial light of the light on the ceiling, the electric light. And the third one, because very probably it will be recorded at night or in the evening, then the lighting will be different. And I'm curious, I'll look myself, of course. I'm curious to see is the readability of the letters, the words here, is it easier in daylight or in the blue light? Is it because the writing, the words, the letters are in blue? So maybe that has a certain contrast effect. Maybe it enhances the contrast. Or, well, I don't know, I'm just guessing. So it will be interesting to see. But from now on, expect 3 sessions, 3 boards worth per day. And who knows, maybe I will buy a bigger board soon, and that will change things quite a bit. Okay, so